Hello, Geometry K students. I am so sorry I'm not able to be at school with you today and teach you. I am at a remote location. Get it from Friday, remote? We talked about that. I'm at a remote location planning lessons with some other team leaders throughout the district. So I can't be here, but I'm with you in spirit and through this recorded lesson. So get your warm-up out. And you can talk about in your tweet of the day how you're a hashtag half full kind of person or a hashtag half empty kind of person. So are you an optimist or a pessimist? And you can write something, you can write a sentence that's optimistic and put hashtag half full, or a sentence that's pessimistic and hashtag half empty. Totally up to you. Y'all can pause the recorded lesson and give people time to share on their warm-up sheet. And then you can go ahead and press play when everyone's had time to do that and the sub has had time to take attendance. All right, here is your warm-up of the day. We learned a theorem on Friday. It was called the exterior angle theorem. And that theorem said that the sum of the remote interior angles equals the exterior angle. So go ahead and use that new theorem and solve for x in this warm-up. You can pause the lesson to give everyone time to set it up, but I'll go ahead and start working it. So we know that these are the remote interior angles, and we add them together. It should equal the exterior angle. I'm going to go ahead and combine like terms. So 4x plus 3x is 7x. 12 plus 19 is 31. And that will equal our exterior angle. Go ahead and solve for x. So this is quite easy. When we move the 7x over, we have 31 equals just plain old x plus 17. We take away 17, and x is 14. Now, it asks us to do something additional. Solve for x and classify the triangle. So we're going to need to plug x back in and find those angle measures. 4 times 14 plus 12. 68, so that's an acute angle. Let's keep going. 3 times 14 plus 19. Oh, 61. And then we can use the triangle sum theorem to find the missing angle. We can add those up and subtract from 180. And we would classify this as an acute triangle because all angle measures are less than 90. All right. Your homework was called Triangle Sum and Exterior Angle Theorem Homework. You had 10 problems. Check your answers. Go ahead and press pause on the recorded lesson so everyone has time to check their answers. I'm just going to go ahead and guess the problems that you might ask about and pretend that you asked about these, and I'll just work these and hopefully this answers any questions that you have. Let's look at number 7 first from this homework. There's a few different ways that you can solve number 7, but I would start by finding the linear pair to 80, which is 100, and then you can zoom in on this triangle right here, and you can use triangle sum theorem to find the missing angle. So add 120 and subtract it from 180 to get your 60-degree angle. So sometimes figures have extra segments like that one drawn in there that you don't really use. We didn't use that segment at all. It really had nothing to do with our problem. Let's look at number 9 as well. Once again, we just want to zoom in to certain triangles. We're not going to use all of the elements of this figure. We're actually just going to use the ones that are going to benefit us. So I can actually, it looks like I can just use this triangle right here. I know that this is a right angle. We know that if we have a straight line and we know we know if those two lines are perpendicular, that they're both right angles. Okay, so now we're just trying to find angle x, and we're just going to add 63 to 90 and subtract it from 180. So we're not using the 27 at all. If you figure it out, you find out that it actually is 27 degrees. And so if you were wondering, this is a right angle, because 63 and 27 and 90 add up to 180. That was just extra information. The answer was 27, and we solved it by just looking at one of the triangles, not the whole figure all at once. Let's get into today's lesson. You may title your notes, Isosceles and Equilateral Triangles. Isosceles and Equilateral Triangles. I won't ever ask you where the root of the word comes from, but I think it's important to know where these words come from, and it helps us understand why they're named what they're named. So if you look at the root of isosceles, the iso means same, and the scalos means leg, so same leg. And we'll get into that in a few minutes. Equilateral, we've already talked about this. Equa, of course, implies equal, and then lateral means of a side, or sided, so equal, sided. So these are the two triangles that we're going to look at closer today. Triangle anatomy. You may pause this and give everyone time to copy this down. I'm going to go ahead and move forward and reveal what all of these parts of the triangle mean. So let's look at the sides first. The two sides that are labeled with the tick marks are called, maybe disappear, they're called legs. The rectangle isn't disappearing like it should. But these two are called legs. There it is. Okay. They're called legs. And the one that does not have a tick mark on it is called the base. So the triangle will have two legs and one base if it is isosceles. Now let's talk about the angles. The angles that surround the base are appropriately called the base angles. That's easy to remember. How do you find the base angles? They're the ones that surround the base, the ones made up of the base. And then the last angle, it's where the two legs meet up, where the two congruent sides meet up. It starts with a V. Anybody? If you said vertex angle, then you are correct. So make sure you copy this down. You need to know the parts of an isosceles triangle. All right, let's look at the pink one first. Triangle tri. Get it? Tri, tri. Okay. Segment TR and segment RI are the legs. Name the base angles. So try to do that without me adding any markings to the picture. Name the base angles. Go. So usually it's easy when our triangle is facing us and it hasn't been rotated or anything, but students have trouble when the triangle is oriented in a new way. And so what I would do first is, since these are the legs, I would add tick marks. And then as you will notice, the base angles are always going to be across the triangle from the legs. So draw an arrow away from the tick marks. And so the base angles are angle T and angle I. So that's how you would locate the base angles. They're going to be across from the legs. Angle A and angle N are the base angles. Name the legs. I'll give you a minute to try that one. All right. Vice versa is true. If A and N are the base angles, then I could look across from the base angles and I would be pointing to the legs. So AG is a leg and NG is a leg. Cool? Cool. First theorem of the day. I actually showed you this theorem a few weeks ago because you needed it for one of our worksheets, but let's write it down officially now. The isosceles triangle theorem. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. So if CA is congruent to CB, then angle A is congruent to angle B. So in other words, when you have, where there is tick marks, there are arcs. Tick marks and arcs go together. You simply look across from the tick marks, and that's where your arcs go. Angle A is congruent to angle B. The base angles are congruent, in other words. The base angles of an isosceles triangle are always congruent. Pause me if people need more time to write this down. Guess what? The converse of the isosceles triangle theorem is also true. Now, some people miss this on their test. You got converse and inverse mixed up. Converse just means we're going to switch the hypothesis and the conclusion. If two angles of a triangle are congruent, then the sides opposite are congruent. So if I give you a triangle and two of the angles are equal, well, then you can look across those angles and you can add tick marks to the side all by yourself. You are allowed to add tick marks. So side AC is congruent to side BC. Okay. Now we have the equilateral triangle theorem. This one's even more straightforward and common sense. If a triangle is equilateral, then it is equiangular. If all sides are equal, then all angles are equal. So you are allowed to add arcs to the angles. Guess what? The converse is also true. I left this blank because it was just getting way too straightforward. If a triangle is equiangular, then it is equilateral. So if 3 angles are congruent, then you can go ahead and add yourself 3 tick marks to the picture. So the original is true and the converse is true for both of those theorems. So I tried to give you like a little picture representation of it. If all sides congruent, then all angles congruent. If all angles are congruent, then all sides are congruent. So there is the equilateral triangle theorem and its converse in pictures. Okay, let's find some missing angles. Now, whenever you have a figure like this, you want to zoom in on angles that are across from the tick marks. So I notice that I'm given this 22 degrees, and it's across from a tick mark. See? It's across from that tick mark. So I go to the other angle that happens to be across from a tick mark, and so I know now that it is also 22 degrees. Now, if I move on to a different triangle, all bets are off. You can't just go to the other triangle and be like, oh, it has 1 tick mark, so the angle across from that one's 22 as well. You can only stay within your own triangle when you use the theorem. When you move to another triangle, they might be totally separate angles. So we're going to use our triangle sum theorem, and we're going to find W. We're going to add up 22 plus 22 to get 44. We're going to do 180 minus 44, and we know W is 136. Then we're going to find the linear pair of 136, which is 44. Now I notice 44 is a base angle. It is across from a tick mark. So the other angle that's across from a tick mark would be right there. To find the vertex angle, to find y, we would do 180 minus 88 because we added 44 plus 44. 92, not drawn to scale. And finally, z would be the linear pair of 44. Linear pair theorem says that z would be 136 degrees. All right. I'll give you a few minutes to think about this one. Notice there is a system of equations here. I know you learned how to do this in algebra. We have not done this yet in geometry, but we started you off with an easy one, so it should be pretty straightforward. I'm going to give you a minute. Please pause yourself and write this down and try to solve this. Okay, hopefully you've paused me and you had plenty of time to solve this. We know that the measure of angle A is x plus y, and the measure of angle C is 4x minus y. Now, you can't just set those equal to each other. I know they're the base angles, and I know that they're congruent, but you can't just set them equal because you have 2 variables. You have an x and you have a y. So we need to know the actual measure of those angles to be able to solve for x and y. What is the measure of angle A? What is the measure of angle C? So if we know that they're congruent, and we've already used up 90 degrees in our triangle, we could do 180 minus 90 divided by 2. Those are 45 degree angles. So we could set this up and we could say x plus y equals 45. 4x minus y equals 45. Do you remember how to solve a system of equations? You just add them together. This is called elimination. We're going to eliminate y. And to be really nice to you guys, we'll always have your systems kind of set up so that elimination is kind of obvious and you're not having to move a lot of stuff around for now. So if I add these together, this should look familiar. X plus 4x is 5x. Our y's cancel. And 45 plus 45 is, of course, 90. 5x equals 90. So then we divide by 5, and we get x is 18. Once we have x, you may plug it into either formula that you want to find y. I would plug it in right here. 18 plus y equals 45. So we just do 45 minus 18, and y is 27. So I snuck a little algebra in there on you that we haven't done yet this year. Hopefully that was okay. All right, for this next part, you do not have compasses out. I didn't want to deal with that while I was gone. So I just want you to watch me, or watch the steps of how you would construct an isosceles triangle, and we will practice when I get back. Okay? Constructing an isosceles triangle. So, your textbook, this is how they teach it. There's more than one way to do this, but this is how we're going to go with because it's consistent with your textbook. So you would take a blank sheet of paper and you would draw an angle. Any angle you want, call it angle A. Preferably not a straight angle. Okay, so you would call it A, and all that is required is that you use a straight edge so that it's actually an angle. Then you would take your compass and you would place the needle on the vertex, which is A, and then you would open up your compass however large you want, as long as you don't go past the end of your angle, and you would draw an arc that intersects both rays of the angle. Where the arc intersects the angle, you label it B and C. You can probably guess what comes next. Use a straight edge to connect point B to point C, and voila, you have an isosceles triangle. Notice how we only did one thing. We just made an arc where our needle was at point A. We started with an angle. So this is just one way, like I said, just one way to construct an isosceles triangle. Do that again. Oh, it says use patty paper to confirm that it is isosceles. I just want to make sure that we know when we're looking at this, though, that AB, this construction, forces AB to be congruent to AC. It doesn't tell us anything about BC. That depended on your angle. So this is not an equilateral triangle. This construction does not create equilateral triangles, only isosceles triangles. Which angles would be congruent? Which ones would be the base angles? Angle B would be congruent to angle C. We know nothing about side BC. That is arbitrary. Okay? Then I would have asked you to repeat the same steps with an obtuse angle. I would tell you to make angle A obtuse. You would draw your arc. Mine is not perfect. You would call it B and C just to practice again. You would connect the dots, and mine is obviously not isosceles, but had I used a compass, that's why compasses work the way they do. It's a radius, and you would have created isosceles triangle ABC. In this one, it would have been more obvious that it wasn't equilateral. It was definitely just isosceles, nothing more. All right, now how would we construct an equilateral triangle? Once again, this is just one of the multiple ways that you can construct one. The book leads you to start off with a circle. So you need to start off with a point, you name it A, and you draw a circle, however large would fit on your page. Then you draw another circle of the same size with center B that goes to the center of the first circle A. That sounds tougher than it really is. And it's hard to see my compass on there. So you want to draw another circle, but you want to make sure that your pencil, when you're drawing your circle, your pencil goes through A. What this is ensuring, if you notice, is that circle A and circle B are congruent circles, so they have the same radii. So we're making sure that all of our sides of the triangle are the same. So we're really just drawing two intersecting circles. They just intersect each other's center. Then you would put a dot at where these circles intersect, and you would connect the center to the center. This is just a radius. This is a radius, and this is a radius. Since they're all the three radii of congruent circles, then you've just created an equilateral triangle. They're all the same length. Woo! Fun stuff. So I already answered this question. How do we know ABC is equilateral? We talked about how they're the radii of congruent circles. Could you use the same construction if you needed the sides to be a given length? How would you begin? So if I said, construct for me an equilateral triangle, and I need it to be exactly 2 inches long. Could you construct me one that is exactly 2 inches long? What would you do when you began? Well, you would take your compass, and you would put your needle here, and you would put your pencil here. You would use the segment I give you, and that's how you would start the construction. That's how large you would open up your compass. Like I said, we'll practice this a little bit when I get back on Tuesday. At home, or we can do it tomorrow, you could see if you can construct a right isosceles triangle without looking it up on the internet. So that's my challenge to you. For the rest of class, you may work on your homework. You need to turn it in by the bell because this lesson was not very long at all. You should have plenty of time to do that. There was something on the homework. At the bottom, it gives you a website to go to teach you how to a different way to construct an isosceles triangle. But on the homework, we left off the .html, and apparently that's kind of important. And so I was just letting you know that you needed to add that to the URL if you were going to go to that website. Okay, be really good, and I'll see you tomorrow.